As known in the previous lecture, then we analyzed the boot sequence until exception level 2. Now, let's explore how the boot sequence can be continued at exception level 1. As you know, after power on, the bootloop will start to execute at exception level 3, and then transition happened from the bootloop to the first bootloader. At this point, the current exception level is exception level 3. And then after running this assembly instruction, then the current exception level is set to exception level 2, and then the second bootloader is starting to execute. But at this point, the bootloader will perform another initialization work to the setup, the fundamental, the system register that is suffixed with EL2, and then it will read the device tree from the storage device to make the Linux kernel to be executable. But at this point, important tasks should be performed in exception level 2. That is the execution of those assembly instructions. So let's analyze this assembly instruction in order to how to set the current exception level to exception level 1. Now, important thing is this assembly instruction can be executed at exception level 2 in the second bootloader. Once those kind of initialization task is complete, this kind of piece of assembly instruction should be executed. Here, this is the sample entry label that is placed in Linux kernel. This is only example label. This base address for this label is written to X2 register. After this assembly instruction, the value of X2 register is stored onto EL1 register. And then this move instruction can be performed. So the binary data is copied to X0 register. Important point is this binary data represent the current exception level as exception level 1. Okay, this is important point. This binary data represent the exception level 1. And then this data, the value of the X0 register, will be written to SPSR2 register by running this assembly instruction. And then after you run ERAD assembly instruction, core will do the two tasks at the same time. The first thing does is to switch the current exception level from exception level 2 to exception level 1, and then the program counter is moved to this address. After this, the assembly instruction is performed, Linux kernel will start to run at exception level 1. So here is the example assembly instruction to set the current exception level as exception level 1. Based on the requirement of your project, and the assembly routine can be customized depending on the features or requirement of your project. Now let's summarize how the exception level can be used during the boot sequence. The first important question is, what is the initial exception level during the boot sequence? The answer is exception level 3. If you refer to the reference manual that describes the boot sequence from the chipset vendor, I'm sure that you're going to see that initial exception level is exception level 3. During the boot sequence, the exception level can start from EL3 to EL2, EL2, and from EL2 to EL1. So most of the chipset vendor implement their boot sequence based on these kinds of the workflow. So this workflow is extremely important because I'm sure that most of the chipset vendor specify the boot sequence based on those kind of workflow.